force collaboration. And there's been many measurements of the growth rate. And you can compare different theoretical models. And at the moment, it seems growth is a little bit underestimated. So in a few papers here and here, they give a summary in this paper that shows that growth is a little bit weaker than expected. So some have postulated this as a possible showing that maybe the gravitational interaction is weaker than predicted from general relativity. What I'm interested in is looking at this Alcock-Paczynski effect and how it can give us information on DAH. How we use this is we have to use a cosmological model to take what we observe, RA, depth, and redshift for each galaxy, and convert that into a co-moving Cartesian coordinate system to then do the analysis. In that coordinate transform, you distort space. Well, you distort the relative position of galaxies. So let's say that in the true universe, these galaxies are separated. This length is exactly the same as this length. If you assume an incorrect cosmological model, then this distance may be different from that distance. You would cause artificial anisotropic stretching or compression of space. So we can actually look for that. This is what would happen. So just as a toy model, if you look, this is a universe with omega matter a little bit higher, omega matter a little bit lower. Sorry, this is all in lambda CDM, flat lambda CDM. Here is if we take the dark energy equation of state to be minus 2.3, and here's a very large equation of state, minus 2.5. And you can see how much distortion this induces on the distribution of galaxies. So we look for that in the anisotropic clustering. So this is a 10% what I call Alcock-Paczynski effect, and it distorts the shape of the contours in this plane. And that's what we aim at obtaining. So the simplest thing to do is just almost count the galaxies in each direction. That's not the easy, that's observationally difficult to do. So what we instead do is we integrate the correlation function over some range. And we integrate it in at different angles. And yeah. Yeah, so this is the integrated correlation function as a function of the angle. And if there's no what I call redshift space distortions, if there's no velocities, then this should be quite flat. This was an incorrect cosmological model. If we assume an incorrect model, this is about W minus 1.3 and W minus 0.7. You can see that this statistic that we've constructed is distorted away from this flat line. So what we try and do is we try and find when this distortion is minimized and we get back to this kind of flat curve. And we used simulations, and this is what we got as our constraint on W and omega matter. And then we proceeded to the real data, and we were kind of actually even in the simulations we were a little bit shocked at how tightly we can constrain these parameters. Because it's doing a little bit better than actually it's doing much better than supernovae alone. Supernovae is in the green, and our method here is in the pink magenta. And if you combine our constraints with what you get from the CMB, we can obtain very, very tight constraints on W and omega matter. So this is actually very, at the moment this is a very model dependent, kind of a model-dependent approach, in that we've just looked at a lambda CDM model and constraining W and omega matter. What we really want is model-independent estimates like D8 and H, and then you can apply it to any theory where you can predict those quantities. And so that's what I tried to do next by only looking at this BEO peak position. So I mentioned that the BEO encodes a physical length scale. So we can look at it, we can try to identify that length scale across our line of sight and along our line of sight. And it should form some arc in this case. So I take 1D correlation functions in each direction, and I just try and find the BEO peak position. And if the cosmology is the cosmology I use to coordinate transform my galaxies, if that's true and that's the real universe, then I would expect these peaks to line up. And if it was incorrect, I would expect some distortion here. Yeah, so I look at the peak position as a function of angle, and using simulations, I can see that there is some scatter, but in general, it should be very flat. And then from there, I can get constraints on DA and H. And this is what this is just a proof of concept at the moment, and using simulations that are equivalent to the Ross survey, we get nice constraints that are model independent on DA and H, and we're applying this method soon to the real data. So I mean that was the main part. I think I don't have much time left. I just want to advertise two other things that you could do with galaxy data. And one is look at the possibility to constrain isocurvature from the early universe. So we mostly assume that the universe started from adiabatic density perturbations, so all the ratios of the particles are equal. But there is a possibility to have isocurvature between dark matter and baryons. And we thought we could look at this by looking at the correlation function, as I mentioned before, same statistic, and also look at the luminosity weighted. So now we use the brightness of galaxies, not just the position of galaxies, but also their intrinsic brightness, and use that weighted correlation function. And we got some interesting results. We actually found that they weren't equal to each other. The correlation functions, the correlation function of the luminosity weighted was slightly higher. And if we fit a model using compensated isocurvature, this red line, then we get a slightly better fit, not statistically significant at this point, but it does show a hint that there is a possibility. And now we're redoing this. This was using BOSS data again, but on a smaller sample. The current BOSS release is much larger, so we're redoing it, and hopefully we can find a more statistically strong signal. Okay, so we'll just conclude. So yeah, we want to go after these quantities because they encode some fundamental information about the geometry and evolution of the background universe, and then yeah, maybe galaxy clustering can also tell us about the early universe as well and the isocurvature. Okay, thank you.
Any questions? Your samples, the galaxy samples, mainly from redshift from 0.4 to 0.7, is that right?
Yeah, that's right.
And what will expect if you extend it to a higher ratio?
Be better. Because what you really want is, you want these quantities at various redshifts, because they are telling you, well, this is a distance, but if we have that distance measurement at various cosmic times, then your ability to constrain models is greatly increased. So yeah, and that's what we're trying to do. In fact, so DESI is a project I'm involved in that's going to look at galaxy clustering out beyond redshift 2, and there's many other surveys doing similar things. So yeah, that's what people are trying.
Any more questions? Two-point correlation. So why do you want to? What that means that you put the two-point correlation to some x, and then you put it after x plus r times squared.
It's just a statistical. So this is the.
This correlation.
Yeah, it's kind of much if you have a field and you want to quantify how its clustering changes as a function of scale, then you could look in a box here and a box there and count the number of galaxies in each, and then move this box around everywhere. So this is a.
These are always fixed.
So.
Up here also the variable.
So to measure the correlation function for 1R, you would take this two boxes separated by R, and then average that around, move the boxes around, holding R fixed. So that's what this X here is, that ensemble, that's the spatial average. But then if you want to look at a different R, you change R, and then do the averaging again.
Thank you very much. Okay, let's move to the next speaker.